Today I'll be proving that if you have a vector space of finite dimension, and any linearly independent set of vectors can be extended to a basis by possibly adding more vectors to the linearly independent set. Okay, so let's say the linearly independent set of vectors is v1, v2 up to vm, and let's say the basis or a basis for this vector space is w1, w2 up to wn. Okay, so I'll begin by proving the following lemma, which will help assist in this proof. And the lemma says, if you have linearly independent vectors, so let's say linearly independent vectors are, say, c1, c2 up to ck, and if you have another vector d, and vector d is not in the span of the c's. If you have a vector d that's not in the span of the c's, then if you add the vector d, if you take a set where you add the vector d to the c's, this is also linearly independent. Okay, so what it's saying is, if you have a linearly independent set of vectors of the c's and you add a vector that's not in the span of the c's, then by adding that vector, the set is still linearly independent. And the proof of the lemma. So we can do a proof by contradiction where we assume we can find lambdas, lambda 1 c1 plus lambda 2 c2 plus dot 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 plus lambda k ck plus lambda k plus 1 d equal to 0, where not all, and also not all lambdas are 0. So it's a non-zero linear combination giving us 0. So we are assuming this new set is not linearly independent for contradiction. So now we will have a look at the case where if lambda k plus 1 is not equal to 0, what you can do is bring the lambda k plus 1 to the other side. And now it turns out we can write, since lambda k plus 1 is not 0, we can write d as a linear combination of the c's like this by dividing by negative lambda. And this is a contradiction because d is not in the span of the c's. So lambda k plus 1 cannot be 0. It's impossible for lambda k plus 1 to not be 0, which means that lambda k plus 1 must equal 0. But now it follows that we have a linear combination of just the c's, which gives us 0, because now lambda k plus 1 is gone. So this is also a contradiction, because since lambda k plus 1 is 0, from our earlier assumption, one of these lambdas from lambda 1 to lambda k must be non-zero, which means the c's are not linearly independent here. However, the initial condition of the lemma is the c's must be linearly independent, and both cases lead to a contradiction, which means this lemma has been proven. So lemma has been proven. Now we go back to the w's and the v's and the w's. Okay, so this is the linearly independent set, this is the basis. So now what I'll do is, if any of these vectors are not in the span of the v's, so if any of the w's are not in the span of the v's, I'll add that w to the set of v's. So an example is, for example, e.g. if w1 is not in the span of the v's, then add w1 to create a new set v1, v2, vm, and w1. Okay, and from the previous lemma we know this is a linearly independent set. And also, since w1 is in this new set, it means now w1 is in the span of this new set. Okay, so now we have a new linearly independent set which we know its span contains w1. Now we can continue with the rest, doing the same with the rest of the w's. So we can, if our current set, if the span of our current set does not include wi, then add wi to form a new set, and this set will, and our current set will always be linearly independent using the lemma, because what we do is we add a wi not in the span of the current set, and the current set is linearly independent, and we form a new set that's still linearly independent. So keep on doing this process until the current set span includes all of w, includes all of the wi's. And this is possible because if we assume the process never stops, this is impossible, because eventually, in that case, we would add all the w's, and if all the w's are there, then the current set span will include all the w's, which means the process will stop eventually, because you eventually keep on adding w's until your current set the span includes all the w's. So now we have a new set. So we have a linearly independent set, which we'll call, let's call it u1, u2 up to, let's say, ut. So this set has all the v's. So we started with all the v's and added w's to create the u's, and it is linearly independent because of how we constructed it and using the lemma. And also its span includes all w's. Okay. Now what we can do is, let's say we have an arbitrary vector x. So any arbitrary vector x in the vector space can be written as a linear combination of the w's. Let's say the linear combination is c1w1 plus c2w2 plus ... plus cmwm or cn. So cnwn. So this can be written, you can also write this in a matrix form as c1 w1 w2 up to wn, and we can write column of C1, C2 up to Cn. But now, since the span of the U's includes all the W's, it means we can write a matrix A. We can write the U's in a row matrix, and then make a matrix A. So we can write it as A11, A21 up to AT1, and going up to A1n and ATN. Okay, we can write a matrix U A and gives us the matrix W over here, and let's say this matrix is C. And this is because, for example, so this we can make it as equal to W. And this is because, for example, we can find coefficients, we can find entries to make linear combinations of U's that give us each of the W's. So for example, here we have W1 is equal to A11 U1 plus A21 U2 plus dot 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 plus AT1 UT. So just using this matrix multiplication as an example, we can find coefficients of the A's that give us W1, and this can be used to construct matrix A. So now what we see is W times C is equal to X, and UA is equal to W. So now if we multiply both sides by C, we have UAC equals WC, which equals X. And using associativity of matrix multiplication, this is the same as U times AC. Okay, and now AC. So this is A is a T times N matrix. C is a N times 1 matrix. So we can write AC is equal to the matrix B, which is a T times 1 matrix. So we can write U times a matrix B, T times 1 matrix B, to give us the vector X. And this is the same as writing a linear combination of the U's to give us X. Okay, so what we've shown is no matter what vector X in the vector space we have, we can write X as a linear combination of the W's, and using the linear combination of W's we can convert it into a linear combination of the U's. So this means the U's are indeed a spanning set. So the U's are indeed a spanning set, and it's also linearly independent. So it's spanning and linearly independent, so the U's form a basis. In previous video we also proved all bases have the same number of vectors, which means T and M have the same size. T is equal to N, because our basis, the W's had N vectors, and our this basis of the U's has T vectors, and since all bases have the same size, then T is equal to N as well. This proves, so we've successfully proven you can add vectors to a linearly independent set of the V's to form the U's, which is a basis. This concludes our proof. Hope you enjoyed this video. Thanks for watching, and I'll see you next time.